Hello, I'm Dan Vredenberg, a student of Professor Fogler's at the University of Michigan and alumni of the Chemical Reaction Engineering course. I'll be doing several of these videos, starting today with a mole balance on a batch reactor. Recalling the general mole balance, and all mole balances that we'll be working with, we consider the terms of the entering, the in, the out, what's being generated within, and then the accumulation. We'd like to apply this to a batch reactor. A batch reactor has the advantage of high conversions that can be obtained by leaving the reactant in the reactor for a long period of time. But it also has the disadvantages of high labor costs per batch, as well as inconsistencies between purities that may be obtained for different batches. Now, we'll start to derive this equation for the batch reactor. Thinking about the in, the out, the generation, and the accumulation, you might want to see if you can come up with the equation that we might have for a batch reactor. Here we have the inlet, the outlet, generation, and accumulation. Now, because we have a closed system, FA naught and FA will drop out, and they'll both equal to 0. Thus, we'll also assume that our batch reactor is well mixed, such that RA can be pulled outside the integral, and the integral of dV will then be V. What this gives us is dNA dt equal to RA times V. This is our characteristic equation for a batch reactor, the differential version. Now, if we wanted to be able to solve for t, for time, we can integrate this and rearrange to get the following. The time necessary to reduce the moles of A from Na naught, the initial moles of A, to Na is the integral of dNA over minus Ra times V. And on this conceptual graph, we can see as time progresses, the moles of A is going to decrease. Now, I'd like to go over an example. Consider the liquid phase cis-trans isomerization of 2-butene. So I don't have to continually say these, we'll write this out symbolically as A goes to B. Now, the reaction is first order in A, which is to say that minus Ra is equal to K times Ca, the concentration of A, and is carried out in a batch reactor in which the volume is constant, which is to say V equals V naught. Our three tasks will be 1. Sketch the concentration trajectory with respect to time. 2. Derive an equation relating the reaction time to the initial and final concentration of A and the rate constant K. And finally, determine the reactor volume necessary to reduce the final concentration to 10% of the initial concentration, and the specific reaction rate, K, is 0.23 minutes to the negative first power. First, we have 1. We'll sketch our concentration of A as a function of T. We can see here our concentration profile is quite simply that we start at time equal to 0 at Ca naught, and as time progresses, we approach Ca equal to 0. For a batch reactor, the mole balance on a species A, and we'll denote J as A, can be shown as follows. dNA dt is equal to Ra times V, as we just derived. For a first order reaction, the rate law, which will be discussed in other videos, which you could look at, is going to be minus Ra equals K times Ca, the concentration of A. Because the volume V is constant, as it is for most all liquid phase reactions, we can then get our terms and rearrange them such that we have the equation here. dCA dt is equal to minus K times Ca. Separating the variables and rearranging will give us minus 1 over K times dCA over Ca is equal to dt. Then, using our initial condition such that at time 0 the concentration of A is equal to the initial concentration of A, we'll get minus 1 over K times the integral from Ca naught to Ca of dCA over Ca is equal to the integral from 0 to t dt. Then carrying out the integration of this gives us that the time necessary is 1 over k times the natural log of Ca naught over Ca. We can also rearrange this to solve for the concentration of A as a function of time. Then we get this equation here. The concentration of A is equal to the initial concentration of A times e to the minus k times t power. And we can see again our concentration of A here as a function of time. Finally, we'd like to calculate t. We'd like to find the time, ti, at which the concentration of A is equal to 1/10 the initial concentration of A, for which k is equal to 0.23 minutes to the negative first power. What we do is substitute Ca naught, Ca, V naught, and k into the equation we have, such we get the following. T is equal to 1 over 0.23 times the natural log of Ca naught over 0.1 Ca naught, which is then arranged into the following. Calculating this out, we get that time is equal to 1 over 0.23 times 2.3, or simply the total time is equal to 10 minutes. I hope this video has been helpful when looking at mole balances on a batch reactor.